The other yield criteria that we very often use is the Tresca yield criteria, about which you must have already heard, which says that yield occurs when the maximum among this, or this becomes equal to the yield stress in shear. So from here, in an uniaxial test, you have sigma, let's say you have sigma 1 is not equal to 0 and sigma 2, sigma 3 equal to 0. Then you immediately see that only this one will be non-zero, and this one will be non-zero. So you will have two, you can immediately see that yield will happen when sigma y is equal to 2 tau y. So according to the Tresca yield criteria, the yield stress in uniaxial tension is twice the yield stress in shear, whereas in von Mises, yield stress in uniaxial tension was given as √3 times the yield stress in shear. So this is a major difference between von Mises and Tresca. Okay, so so now um, yield will occur when um, the difference between any two uh, of the yields of the principal stresses at a point is equal to tau y. So we have to take the maximum principal stress, the minimum principal stress, take their difference, half it, and set that is equal to tau y, or we can just take sigma max minus sigma in and set that equal to sigma y. Either case, we are satisfying the Tresca yield criteria. So if you compare the Tresca with von Mises, this is how the comparison goes. We have already seen that the von Mises yield criteria in the principal stress space is a cylinder with its axis along the hydrostatic line, which is sigma 1 equal to sigma 2 equal to sigma 3. This is your pi plane, which is the plane given by sigma 1 plus sigma 2 plus sigma 3 equal to 0. This is the pi plane. And this is the von Mises yield criteria. So when a stress state hits this cylindrical surface, it yields according to von Mises yield criteria, whereas the Tresca is a hexagon circumscribing the von Mises circle. So the Tresca yield criteria is a hexagonal prism, which circumscribes the von Mises cylinder. You can project this onto the pi plane. So you can put your eye here and draw a projection on this plane. So when you project on the pi plane, the sigma 1, sigma 2, sigma 3 axes, which are orthogonal in the 3D principal stress space, are projected onto these lines. This is sigma 3, this is sigma 1, and this is sigma 2, which are separated by 120 degrees. Also, you must remember that on the pi plane, sigma 1 plus sigma 2 plus sigma 3 is equal to 0. That is the definition of the pi plane. So this means that the hydrostatic stress, sigma h, which is sigma kk by 3, is also equal to 0. So all the stress states that reside on the pi plane are necessarily deviatoric stresses whose hydrostatic components are equal to 0. If you go above the pi plane, if you come above the pi plane, then the hydrostatic stress increases. So you add a constant hydrostatic stress to each component of your principal stress. If you go below the hydrostatic plane, you subtract hydrostatic stress from each component, or in other words, you apply a compressive hydrostatic stress. So below you have addition of compressive hydrostatic stresses. Above the pi plane, you add positive tensile hydrostatic stresses, but on the pi plane, hydrostatic stress is equal to 0. So hydrostatic stresses, all deviatoric stress states, all reside on the pi plane. Now, how do we find the projection of a stress in terms of its principal components on the pipe plane. So projection, a stress in terms of its principal component in the principal space, if we take the base vectors to be E1, E2, E3 is this. So you can describe a stress as this in the 3D uh, 3D space of principal stresses. So once you do this, you also have the hydrostatic line which has unit vectors. This is the unit vector along the hydrostatic line. So first let's find the hydrostatic part, which is sigma dot h, which will give you sigma 1 by root 3 plus sigma 2 by root 3 plus sigma 3 by root 3. This is what you will get. Then what you can do is, to get the hydrostatic part of the stress vector, you can take the original vector and subtract the part along the deviatoric along the hydrostatic line. Sorry. So you take the stress vector, which was this, and subtract the part along the hydrostatic line. So you get sigma 1 E1 plus sigma 2 E2. So once you have this, you can immediately see that you will have sigma 1 prime E1 plus sigma 2 prime E2 plus sigma 3 prime E3 as the projection of a stress vector expressed in terms of the principal values and the principal directions. These are the principal directions and these are the principal values. So I can express this stress as I've expressed this stress as a vector, and its projection on the pipe plane is this, which turns out to be whose components turn out to be the deviatoric components of sigma 1, sigma 2, sigma 3. So what we have proved is that only deviatoric stresses reside on the pipe plane. Let me erase this. Okay, so now take a vector which was originally along the one direction. So if I take a vector which was originally, the stress vector was sigma 1 E1, so its components on the pipe plane would be sigma prime given by the deviatoric part of this. So the deviatoric part of this would be 2 by 3 sigma 1 E1 minus 1 by 3 sigma 1 E2 minus 1 by 3 sigma 1 E3. So this would be the deviatoric part, and this would, the unit vector along this. So if I say the unit vector, that would be 1 by root 6 2 E1 minus E2 minus E3. So that is this vector. So this is the projection of a uniaxial of a stress state which has only one principal value. Other principal values are 0. For that stress state, this is the projection on the pipe plane. Similarly, this vector would be 1 by root 6 minus 1 minus 1 2 and this vector would be 1 by root 6 minus 1 to minus 1. So these would be the vectors along the uniaxial directions, projections on the pi plane. So now if you look down on the pi plane, if you project the von Mises and the Tresca on the pi plane, the Tresca would look like a perfect hexagon, and von Mises would be a circle which is inscribed inside the hexagon. And any point on this plane represents, as we have already seen, a deviatoric state of stress. So the magnitude of this, so any point on this is represented by a vector which is sigma 1 prime E1 plus sigma 2 prime E2 plus sigma 3 prime E3, and the magnitude of this vector is sigma 1 prime square plus sigma 2 prime square plus sigma square. Remember, J2 is defined as half sigma ij prime sigma ij prime, and when ij are the principal stresses, this would be defined as half sigma 1 prime square plus sigma 2 prime square plus sigma 3 prime square. So this quantity is equal to 2J2, okay, and therefore this is the magnitude squared actually. So the magnitude of this would be root 2J2. So this magnitude is always equal to root 2J2 on the pi plane. Okay, and this angle from the sigma 1 direction is called the Lode angle, and the Lode angle can also be found by taking a dot product between this vector and this vector. Let me erase this. So if you now write the Lode angle, this is the Lode angle. So cos theta is given by this, and then we can express this cos theta in terms of cos 3 theta with a formula which is dependent on J3 as well as J2. So this angle theta, 3 times theta of this angle, the Lode angle, which is measured from sigma 1, is dependent on both J3 and J2. What that means is that obviously the von Mises is a circle on the pi plane, so it's not a function of this angle. It's not a function of this angle. The shape of the yield function is independent of this angle. Therefore, for von Mises does not have a dependence on J3, does not have a dependence on J3, which is obvious from the definition of the von Mises yield criteria that we had earlier. So this is the definition. This was the definition of von Mises criteria, and we saw that it's dependent only on J2 and there's no dependence on J3. However, that's not the case with the Tresca criteria. The Tresca criteria is dependent on this angle. The shape is dependent on this angle, and therefore there's a dependence on J3. So though Tresca criteria is expressed in terms of the maximum principal shear stress, you have to remember that this actually hides a dependence on both J2 and J3, and that is shown in this slide. That was the purpose of this slide. So Tresca is dependent on both J2, J3. Von Mises is dependent only on J2, and therefore von Mises is the shape of the von Mises curve, von Mises yield function is not dependent on the Lode angle. Okay, so However, because we have assumed isotropy, which means that the material does not know which is sigma 1, which is sigma 2, which is sigma 3, I can label them whichever way I like. So I can switch the axis and still the shape of the yield function will be the same. Also, I have assumed that yield stresses in tension, that is, say, tension in sigma 3 direction, yield happens here. Compression in sigma 3 direction, yield happens here. So the yield stress in tension, which is this, is same as the yield stress in compression, which is this, right? Since we have assumed this, then both Tresca and von Mises have to have a six-fold symmetry. That means I will not be able to distinguish if I switch sigma 1, sigma 2, sigma 3. I will not be able to distinguish if I flip this along, say, this line or this line or this line. So a six-fold symmetry is indicated, and therefore if I know the shape of one sector, let's say this one, I know the shapes of all the other five sectors. So I need to basically know the shape of the yield function on the pi plane from load angle equal to theta equal to 0 to a load angle of theta equal to 60 degrees. So that's what I need to know. Now, these two are somewhat special situations, and the way I have defined the load angle, I have defined it from the sigma 1 axis. This is the sigma 1 axis. I've defined it from there, and in this red region, sigma 1 is always the maximum principal stress, sigma 2 is the intermediate, and sigma 3 is the least. So this is valid in this red region. It's not valid in every region, but every region is just a rotation of this red region. So we should concentrate on this red region only. At theta equal to 0, I know this vector is the deviatoric vector corresponding to a uniaxial stress state along sigma 1. So its components are 2, minus 1, minus 1. So along this line, along theta equal to 0, I have the situation where sigma 1 is greater than sigma 2, which is equal to sigma 3. Sigma 2 and sigma 3 are the same. Similarly, along this direction, this this vector is along a uniaxial stress state of sigma 3. So its deviatory components are 1 by root 6, minus 1, minus 1, 2. And the negative of that is 1, 1, minus 2. So on at this point, what I have is sigma 1 is equal to sigma 2, which is greater than sigma 3. So this is the state of stress. This is always the state of stress along the theta equal to 60-degree line. So what this means is, what this can be thought of as the first state of stress. So I can think of it as a box in the principal directions, pillbox in the principal directions, with sigma 3 as the hydrostatic stress on all sides. So sigma 3 is a hydrostatic stress, imposed on this pillbox, and on the one direction I have an additional sigma 1 minus sigma 3 tensile stress superimposed. So in the one direction I have a sigma 1 minus sigma 3 superimposed, and sigma 3 is the hydrostatic stress all around. So this can be thought of, this can be thought of as hydrostatics plus tension. So this point represents stress states that can be thought of as hydrostatic plus tension. Whereas at this point, I can do the same thing, but a little differently. So I can put sigma 1 everywhere as the hydrostatic stress. And then in the 3 direction, I can put a compressive stress sigma 3 minus sigma 1. Sigma 3, remember, is the smallest. So sigma 3 minus sigma 1 is compressive. So I can put a compressive state. So this state is a hydrostatic stress state plus a compression. So all stress states right above the pipe plane and below the pipe plane, but at the same angle theta, will also be considered as hydrostatic plus tension, whereas all stress states above the pipe plane, below the pipe plane, and on the pipe plane um, at theta equal to 60° will be considered as hydrostatic plus compression. So it is important, these are some nitty-gritties of the yield surface geometry, but it is important to be able to visualize the yield surface and make sense of what is going on. Yield surfaces that we have learned, Tresca and von Mises, are somewhat simplified yield surfaces. These are yield surfaces that are mainly used for metals and some other materials as well, but these are yield surfaces where the material is assumed not to have any effect on plasticity of the hydrostatic stress, which is not always true. These yield surfaces also have tension compression symmetry, which is also not true. So once we bring in all those subtleties in the yield surface, dependence on hydrostatic stress of yield, um, tension compression asymmetry, all those things, the yield surface shape looks much more complicated than Tresca and von Mises. And in those situations, sometimes being able to visualize the yield surface and able to visualize what is going on is important. So that's why I spent some time on this. So now we move to two dimensions and look at thin plates, thin sheets, where the third direction is the thickness direction. In third direction, sigma 3 is equal to 0. It's a plane stress situation. So if sigma 3 is equal to 0, we can put the Mises condition. We can just put sigma 3 equal to 0, and we can write the Mises condition in the principal, in terms of the principal stresses, and this is what we get. So in the original Mises yield condition that we had looked at some time back, so in this yield, so this was a Mises and J2 was 1/6 of this. So in this yield condition, we put sigma 3 equal to 0, and we get this equation, which is obviously the equation of an ellipse. So in this plane, in this three-dimensional space spanned by the three principal directions of the stress, E1, E2, E3, we have called them. So in this space, you take a subspace of that, which is sigma 3 equal to 0. So that's the sigma 1, sigma 2 plane, and you can now draw the yield surface. You can now draw this Mises yield surface on the sigma 1, sigma 2 plane, and this is how it will look like. So if you pull uniaxially, if you apply uniaxial stresses along sigma 1 or sigma 2, you will yield at this point if you are in tension, at this point if you are in compression, this point if you are in tension, this point if you are in compression. If you apply a biaxial state of stress, sigma 1 equal to sigma 2, then you are going along this line and you will yield here in tension if both of them are in tension. And then, so these are the biaxial states of stress. On the other hand, if you apply pure shear, so you apply a stress state which is, let's say this, you apply a stress state which is this, then you get sigma 1 minus sigma 2 or sigma 2 minus sigma 1. by 2 as the maximum, as the principal stresses. So so this shear stress is either twice this shear stress is either sigma 1 minus sigma 2 or sigma 2 minus sigma 1, and these are those locations. So you will be moving along these directions. Start from here, you apply pure shear, move along these directions, and you will hit these points. They will cause yield here. So depending on how you deform your sheet, if you deform it in uniaxial tension, you will hit yield here. If you go in biaxial, you will hit yield here. If you go in shear, you will hit yield here or here. Okay. So let us do a few problems. So in these problems, we are just concerned about when plasticity ensues. When does it start? We are not really concerned about what happens after plasticity starts. That we will look at a little later, after we have learned uh, the entire theory of plasticity in small strains. So right now, what we are trying to find out is this is a thin walled cylinder. It's closed at the ends. It has a pressure P inside, and we want to find out the pressure P equal to Pu at which the walls will yield. So these yielding problems are basically elasticity problems, where you have to look at the elastic state of stress and then figure out when does that state of stress satisfy the yield condition, and according to von Mises or Tresca, whatever you are asked to do. So here we know thin walled cylinder closed at the ends. The stresses are hoop stresses, which are P d by t 2t, and pd by 4t is the stress in the axial direction. So we know that these are the stresses for a thickness of t. And now if you use the Tresca yield criteria, you have to remember that sigma, so this is a principal state of stress, and sigma 1 is the maximum, sigma 2 is the intermediate, and sigma 3 equal to 0 is the minimum. So if you have to calculate the principal maximum principal shear, you have to take sigma 1 and sigma 3, which is what we have done. So the Tresca yield criteria is maximum principal shear stress is equal to tau y, which is equal to the uniaxial yield stress divided by 2, which gives me pressure at yield of this. So if you increase the pressure, you hit this pressure, your walls will yield, and that's all that you have to do in this problem. Okay, so we will do two other problems. So here's the second one. This is a cantilever beam subjected to a force here, and then the bending moment and shear force diagrams you can easily draw. The bending moment, the shear force diagram is constant, F constant all over the beam, and the bending moment diagram is a triangle which is equal to F times L at the built-in edge. Now, the bending moment can be written as a function of x1. This is x1. So as a function of x1, you can write it like this. It is equal to minus FL at 0, x1 equal to 0, and is equal to 0 at x1 equal to L. That's obvious from this. And then according to Euler-Bernoulli beam theory, we know that the stresses, only sigma 11 is the relevant stress, and that is given by mx1 into x2 by I. Let us assume that this beam is a rectangular cross section. So as you go in this direction, x2 increases, and as you go in this direction, x2 decreases. So this is your stress. There's only one stress. So the principal state of stress is sigma 1 equal to sigma 11, and then sigma 2, sigma 3 is equal to 0. This is your state of stress. So to apply the Tresca yield criteria, you have to just use sigma 1 and one of these two, both of these are 0. So if you apply the Tresca yield criteria, then then you can imagine that um, the maximum, the first point where yield will happen when mx1 is the maximum and x2 is also a maximum, which will happen at this point. So m is maximum on this cross section, and then you have this linear variation on x2, and x2 is maximum here. It will happen probably in compression here and in tension here at the same instant. So these are the points from which your plasticity will start. These are the points that are going to yield first. So you have to put x2 equal to plus minus c to get the force that will cause yield at this point or at this point. Both will happen simultaneously. So this is the force that you will need according to Tresca criteria in order to cause yield, provided your beam is rectangular and has a height of 2h and a breadth of b. Okay, so this is your yield. This is your yielding load that will cause yield at those 2 points that we mentioned. So let us also look at the cylinder problem. We'll take the cylinder problem. We will do a little more on the cylinder problem later. But first, let us try to find for this thick cylinder what is the internal pressure that will cause yielding. Okay, so this is the elastic solution. You have already done the elastic solution in your elasticity courses, so I'm not going through this, but the derivation is all there. I guess you will recognize these two relations. So in the problem that we did in our elasticity courses, this was the form of the stresses, the two stresses sigma rr and sigma theta theta. So at any point r, if I draw this separately, this is sigma rr and this is sigma theta theta. All other stresses are 0. So any point on the wall is in a principal state of stress, which has sigma r and sigma rr and sigma theta theta. There's also a sigma zz, provided this is a very long cylinder or it's closed at the ends. So if you have a cylinder which is closed at the ends, then you have a sigma zz as well, but you don't have shears. So this is a principal, every point is in a principal state of stress. It has either sigma rr, sigma theta theta, or all three of sigma rr, sigma theta theta, and sigma zz. Okay, so this was the variation of sigma rr and sigma theta theta that we had done earlier in our elasticity courses. The derivation is also there, and now sigma rr at r equal to 0, at r equal to a, sigma rr at r equal to a is given to be equal to minus p. So the pressure at the inner radius is given, and we have to find what is the maximum pressure that this can sustain before it yields. So sigma rr at a is equal to minus p, sigma rr at b is equal to 0, and then we can solve for these two constants a and b, and these are the two solutions that we get, sigma rr and sigma theta theta. These are the solutions that we get. Now based on these solutions, you can find sigma zz. I leave that to you to find out, but here is the result. So sigma zz would be different if you have closed ends. It will be different if you have a very long cylinder with plane strain or with open ends. So for these different cases, you will have a different expression for sigma zz. Please try to derive that. So for open ends, alpha is equal to minus nu, so sigma 33 will be equal to 0. For plane strain, it will be 2 nu divided by this for a very long cylinder, and if you have closed ends, then alpha is 1 minus 2 nu, so 2 nu cancels. It will be 1 by b square a square minus 1. So these three different cases for sigma zz, given that sigma rr and sigma theta theta are given by these expressions, is actually easy to derive. You can derive them, and once you have derived them, you have to realize that sigma 33 turns out to be the intermediate stress. So the maximum and minimum are actually given by sigma rr and sigma theta theta. So in all cases, sigma 33 turns out to be the intermediate stress, and therefore when you do the Tresca yield criteria, you use sigma theta theta minus sigma rr and find the internal pressure at which yield happens uh, based on sigma theta theta minus sigma rr by 2 equal to tau y or sigma y by 2. So that is what this is, sigma y. I'll change it in the notes. This is sigma y. So you take this equal to sigma y by 2, and this is pu, and from there you get this expression for pu. Yield obviously starts at the inner edge. So it starts at the inner edge when P reaches PU. Yield condition is satisfied at the inner edge, and then propagates outwards. The propagation we cannot deal with at the moment. We can only deal with the initiation. So in order to deal with the propagation, in order to figure out how this is going to spread as you keep increasing P beyond PU, we will have to understand how the stress strain relations that we have learned in elasticity are modified when we have plasticity also active. Okay, that is in the next lecture.